Hi, welcome to the Olympiad geometry. Let's continue our study. Before we start, if you think this video is helpful, please click the like button, comment, share, or subscribe to the channel. Thank you. Today we're going to talk about a new chapter. It's called radical axis. So first we look at the concept of power in the geometry, and then we look at the concept of radical axis. Okay. Draw any secant line from point A to a circle. The product of the two line segments from A to the point where the secant intersects the circle is called the power of A with respect to the circle. I think we're already familiar with this from the basic geometry class that so this is point A, this is a circle O. If we draw a secant that intersects the circle onto point B and C, then we call AB times AC to be the power from A respect to the circle O, right? And if we draw another tangent line from A to the circle O, let's call the tangent point to be D, then we know that AB times AC equals to AD squared. Right, that's all from the basic geometry class. So the conclusion 1. The power of A with respect to the circle O equals to the difference of squares of OA and the radius of OD. So because we know all the power from a point A respect to the circle O is a constant, right? So we can have AB times AC, that's a power. We also can use this one, connect AO and extend it to intersect the circle O to E, right? So here, the intersection point, we can call it F. We know that AB times AC equals to AF times AE equals to AD squared, right? And AF times AE can be rewritten as AO minus R, right? AF is AO minus the OF is the radius R, times AE. What is AE? That is AO plus OE. OE is R, so AO plus R equals to AO squared minus R squared. Right, so that is saying the power of A with respect to the circle O equals to the difference of squares of OA and the radius of circle O. Conclusion 2. For two given circles, the locus of points with equal power to both circles is a straight line that perpendicular to the line connecting their centers. And we call this perpendicular line as radical axis, right? That's a locus of points with equal power to both circles. So let's prove it. So first, we draw two circles. We draw two circles here. This one we call it O1, and we draw another circle here. This one we call it O2. Right? It doesn't matter. It doesn't matter the position of the two circles, whether their intersection or they are separate or they're tangent. Right? So let's think about this distance. We call it D. Right? And we know there is a point A that satisfies the power from A with respect to the circle O1, and the power from A the power of the A with respect to the circle O2 would be equal, which means that A01 square minus R1, so this is R1, and this is R2, right? That means A01 square minus R1 equals 2. A02 square minus R2 square, right? That's what we learned. The power from the power of A with respect to O1 equals to A01 square minus R1 square. And similarly, the power of A with respect to circle O2, that's A02 square minus R2 square. And we force them to be equal. Then we know that A01 square minus A02 square equals 2. R1 square minus R2 square. Notice that since the circles are given circles, so we know that R1 square minus R2 square is a constant, which means A01 square minus A02 square is constant. So let's just find the projection from A to O1, O2, call it as D, right? So what is A01 square? A01 square can be rewritten as O1D square plus AD square, right? That is A01 square minus A02 square is O2D square plus AD square. So we got O1D square minus O2D square, right? AD square cancelled equals 2. R1 square minus R2 square. And we extend this O1D minus O2D times O1D plus O2D equals to R1 square minus R2 square, right? And we know that O1D plus O2D, O1D plus O2D, that is O1, O2, which we can represent it for the little d, right? So we got O1D minus O2D equals 2 R1 square minus R2 square divided by D, which is O1D plus O2D, right? So now we know that O1D plus O2D equals to D, and we know that O1D minus O2D equals to this one. Notice that R1 square minus R2 square divided by D is still constant, right? So we got O1D equals 2 D plus R1 square minus R2 square divided by D divided by 2, right? So it equals to D by 2 plus R1 square minus R2 square divided by 2D. So what is D by 2? That's a midpoint from O1 to O2, right? Let's call it midpoint M, right? So it equals to O1M, which is midpoint, right? Plus R1 square minus R2 square divided by 2D. Right, for a given circle, we already know that R1, R2, D, they are all constant. So, which means this is constant, which means that the distance from O1 to the projection point of A to O1, O1, O2 is constant, right? Because this is constant, this is constant. So now we know that all the points that satisfy the power with respect to O1 and with respect to O2 has a same projection point to O1, O2, which means all of the locus of these points should be on this line, right? And now we actually just read about the property 1, 2, 4 together, and then we think about property 3. So for property 1, if two circles intersect, their radical axis is a straight line. It is a straight line containing their common chord, right? It is saying that if we have two intersection circles, then this line, that is common chord, right? And we know that common chord is perpendicular with center connection O1, O2, right? So it seems that the radical axis contains the common chord, which is fairly simple to prove, right? Because when we do this provement, it doesn't matter whether two circles are intersection or separate or tangent, right? So for the case, the intersection, then we know the intersection point has a power respect to O1, O2 equals to 0, right? Because it's A O square minus R square equals to 0, right? Always. So, and we know that one line can be defined by 2 points. We already have 2 intersection points, so we know that this must be the radical axis. And similarly for the tangent case, right? For the tangent case, because we already know that the radical axis has to be perpendicular with O1, O2, and we know this point here has an equal power to O1 and O2, right? Equals to 0. So we know that if we connect O1, O2, we draw a line that passing through the tangent point and also perpendicular with O1, O2, that is the radical axis. And we know that since it's perpendicular with O1 to this connection, so here is 90 degrees, then we know this is a tangent line, right? So that's for the second case. If two circles are tangent to each other, the radical axis is a common tangent passing through their points of tangency, right? Let's just look at the fourth first. If two circles are separate, the midpoint of their 4 common tangent lies on the radical axis. This property actually we already proved that in the previous chapter, right? Remember that if we have a we're talking about the separate case, right? I mean, for the, let's just find it here. For the intersection case, this is also the midpoint, right? Because the midpoint satisfies that from here, let's call it A, B, C, D, right? And E. We know that A, B, because A is the midpoint of BC, so AB squared equals to AC squared equals to AE times AD, regardless which circle we're talking about, right? So then we know that is that is saying the midpoint of common tangent. So the midpoint of the line segment from the common from the common tangent lies on the radical axis. Okay, so similarly for the separate case, that is one common tangent. So just because its midpoint, which means from this midpoint, let's say it's A to B and C, that AB squared equals to AC squared, right? That's the definition of the point on the radical axis. So it must be on the radical axis, and also for the inner tangent, right? The midpoint also satisfies that GE equals to GF. So that means GE squared is a power from G to with respect to O1, and the GF is power with respect to O2, and they are equal. So we know that for midpoint are all on the radical axis. So let's see the property 3. Property 3 is saying that for 3 circles, their pairwise radical axes either intersect at a single point or are mutually parallel. So we think about the case that the first case that 3 centers are not on the same line, so it doesn't matter they're intersecting each other or separate. I just draw it in the intersection way because it would be easier to find the radical axis, right? So for O2, O1, and O3, right? So for O1, O2, this is this line. Let's call it L1. L1 is a radical axis of circle O1 and O2. And we know that this line, L2 is, see this point and this point, right? L2 is a radical axis for O1 and O3, right? And these two lines has a intersection point. Let's call it P, right? So we know that the point P has the same power because it lies on the L1, so it has the same power with respect to O2 and O1. And also it has because it lies on the L2, so it has the same power with respect to O1 and O3, which means that P has the same power with respect to O3 and O2, right? That means P must be on the radical axis of O2 and O3. So 3 lines are concurrent. And for another case that the center of the circles lie on the same line, right? So we know that the radical axis between O1 and O2 must be perpendicular with O1, O2. And similarly, for the radical axis between radical axis for O2, O3 must be perpendicular with O2, O3. So they are in parallel. And also the radical axis for O1 and O3 must be perpendicular with O1, O3. So all these 3 lines are perpendicular to O1, O3, which means all these 3 lines are in parallel. Okay, that's a basic concept and properties of the radical axis, but this is a very interesting concept and it's very useful. We will talk about more about the examples and solutions in the future videos. Okay, I hope you like this video. See you in next one. Thank you.